positive. When it's in compression, the stress, the deflection, the strain, and the load are all what? Negative. I want to highlight this. This is important. Why? Because we just did what? We just did static analysis where we say positive is anti-clockwise, positive is going towards the right, positive is going up. For elastic deformation, that does not work anymore. It all depends on whether the structure is under tension or if the structure is under compression already. This you have to bear in mind. A lot of students have problem with this topic because they're assuming going towards the right is positive, going up is positive, anti-clockwise is positive. No, no more. When you do elastic deformation, where deflection is equal to PL over AE, okay, it's all based on tension and compression. Okay, so here we go. So for cable B, okay, for cable B, right? So deflection of cable B is equal to FB LB divided by AB with the Young's modulus. So we are given all this information. So now we have opportunity to find what is our FB now. Okay. So deflection of point B. So FB multiplied by the LB length is 4 divided by the cross-sectional area. So the cross-sectional area, so the cables are pi. The radius is, I'm looking for the radius now. So the radius is 0.006. Okay, not 0.6, 0.006 squared. So pi r squared. Then divide by the Young's modulus, 200 times 10 to the power 9. So when you work this out, okay, so it will be 4 divided by shift pi divided by 0.006 squared divided by 200 to the power 9 is equal to 176.83. So it's equal to positive 176.839 times 10 to the power minus 9 FB, right? So this is your equation number 3. So positive over here means it's under what? Tension. Okay, like how we have drawn our free body diagram, right? So it's under tension, that's why we call it positive. And then at cable C, so deflection of C is equal to FC LC over AC divided by E. So everything is the same except FC. Now the length is what? 2. Okay, the rest of the expression is still the same. The cross-sectional area is the same. Okay. So this will come out to be positive 88.42 times 10 to the power minus 9 FC. Okay. So this is not really good yet, yes or no, right? Why I say it's not really good is we have deflection now, right? We have equation that is deflection related to what? FB and FC. So this is not. So the next thing that we're going to do is we are going to relate. Okay, so we are going to relate that the deflection of point B, right, to deflection of point C based on geometry. Okay, so i.e. we're going to relate Okay, we're going to relate equation 3 to equation what? To equation 4. Okay, we're going to relate equation 3 to equation 4. And this is where we make an assumption earlier that really will help. So the assumption that we make earlier is that we assume, right? We assume a member ABC, right, to be a rigid body. So this is what we assume. So we have our member over here. So this is our point A, this is our point B, and this is our point C. And because we make the assumption that it's a rigid body, that's where things simplify ginormously for us. It makes our life so much easier, and the software is just crap. Okay, so we know that over here, right, this is your B prime, and over here this is your C prime. Now this is exaggerated. Okay, this is exaggerated. The deflection is exaggerated. So we are aware that the distance from here to here, this is your delta B, and the distance from here to here, this is your delta what? C. So from here, because we assume, we are fortunate enough that we assume that ABC is a rigid body, then we can form another statement that we now know that point A, B prime, and C prime, okay, are on the same gradient. So some of you might say they are on the same what? Or slope. So this makes our life easier, okay? So that's why we make the assumption in rigid body, okay? If not, you're going to have mayhem, okay? You're going to go crazy. So we know that the gradient real straightforward, where gradient will be equal to change in y divided by change in x. So we know that based on transformation, this is your x direction and this is your y direction. So this we are more focused on magnitude, okay? So this will be equal to 6 divided by delta B, and this will be equal to 9 divided by delta C. Okay, so they are on the same what? They are on the same gradient. Okay, so we know delta B, so this is my equation number 5. Right? So we know our delta B, our delta C. So this is from equation number, this is from our equation number 3. This is from our equation number what? Our equation number 4. So from here, give me another 10 minutes, okay? And we'll be done. Okay. And you can go to sleep. You don't need to drive, right? So over here, now we can write the expression where 6 divided by your delta B is 176.839 times 10 to the power minus 9 FB. And this is equal to 9 divided by 88.420 times 10 to the power minus 9 FC. So you have an expression where FC will be equal to 9 over 6 multiplied by 176.839 times 10 to the power minus 9 and this will be your FB, and then you divide the whole thing by 88.420 times 10 to the power minus 9. So from here, you realize that FC will be equal to 3 times FB. So this will be your equation number 6. Okay. So from here, we're going to substitute equation. Now, this equation, you only focus on magnitude, yeah? Okay. You only focus on magnitude, the relationship. Okay, there's no plus minus for this. And there's no plus minus, and it's also because both of them, the deformation is in the same direction. Okay, so over here, just focus on the magnitude. So we're going to substitute equation 6 into equation number 1. So if you look at equation number 1, you have, so equation number 1 is 6 FB, right, plus by 9 FC will be equal to 465 times 10 to the power 3. Okay, so this is your equation number 1. So you substitute that over there, so you will have 6 FB plus by 9 multiplied by 3 FB is equal to 465 times 10 to the power 3. So that will be equal, so 9 times 3 is 27 plus 6 is 33 FB. And then this will be equal to 465 times 10 to the power 3. And then finally, FB will be equal to 14091 Newton. Okay. And then now you can find FC will be equal to 3 times of your FB, right? So this will be equal to 3 multiplied by 14091, and the outcome will be 42273 Newton. Okay. And then finally, the last part, which we already have the equation already. So for the next part of the question, we're going to find the deflection of point C. Okay. And one more thing that we'd like to ask is, will the cable support the load? Okay. So now we're going to use equation number 4. Okay, so we're going to use equation number 4 to find the deflection of point C. So deflection of point C is equal to FC. Okay, so FC we found out to be 42273. Okay, so PL, the length is 2 meters, divided by the cross-sectional area, so it's 113.097. So that is the cross-sectional area that we have been calculating, divided by the Young's modulus. So the deflection will be equal to 3.738, okay, times 10 to the power minus 3 meters, or 3.738 millimeters, and it's going towards the left. And then you want to calculate the stresses of the cable at point C. So it's equal to 42273. So this one, what formula I use based on stress is equal to FC divided by area of the cable. So this will be equal to 42273 divide by the cross-sectional area, 113.097 times 10 to the power minus 6. So this happens to be 373.776 times 10 to the power 6 Pascal. So we realize that the stress at C is lower than the stress yield